Hello students, we are going to discuss test 16 today. The topic was EMI and alternating current. In the first question, for an LC circuit, the inductance is given 1 microhenry and the capacitance is 0.01 microfarad. We want to find the electromagnetic wave, its wavelength lambda. Here frequency is given by 1 upon 2 pi under root L C. We know that C is equals to F lambda. Here C is the speed of light in vacuum. So lambda is written by C divided by frequency. So lambda will be 2 pi into C. Here the C is speed of light in vacuum under root L C. So 2 pi into 3 into 10 power 8 into inductance is 1 microhenry into capacitance is 10 power minus 8 farad. Simplify this, we'll get wavelength is equals to 60 pi, that is 188.4 meter. So option 3 is correct option. In question number 2, we want to find the range of frequency of visible light. Here C is given by F lambda. So frequency is equals to C divided by lambda. The wavelength of visible light is in the hundreds of nanometer. So 100 into 10 power minus 9 meter. That will be 10 power minus 7 meter. Speed of light is 3 into 10 power 8 meter per second divided by lambda in the order of 10 power minus 7. So frequency is in the order of 10 power 15 hertz. So option 1 is correct option. In question number 3, a plane electromagnetic wave of frequency 40 megahertz, that is 40 into 10 power 6 hertz, travels in a free space in x direction. At some point and at some instant, the electric field has the maximum value 750 Newton per Coulomb in y direction. We want to find the magnitude and direction of magnetic field. Here velocity is perpendicular to electric field and velocity is perpendicular to magnetic field, as well as E and B both are also perpendicular. As wave is traveling in x direction, electric field is in y direction, so B will be in z direction. C is equals to E by B, so magnitude of B will be equal to E by C. E is 750 divided by 3 into 10 power 8. So B is equals to 2.5 microtesla. So option 3 is correct option. In question number 4, it is given that a plane electromagnetic wave of wave intensity 6 watt per meter square strikes a small mirror of area 40 centimeter square, that is 40 into 10 power minus 4 meter square, which is held perpendicular to the approaching wave. We want to find the momentum transferred by the wave to the mirror. As the mirror is the perfectly reflecting surface, the momentum transferred is given by 2IA by C. So 2 into 6 into 40 into 10 power minus 4 divided by 3 into 10 power 8. Simplify this, we'll get P is equals to 1.6 into 10 power minus 10 kg meter per second. So option 4 is correct option. In question number 5, We want to find the magnetic field between plates of capacitor at distance 1 meter from center. The electric field variation is given by 10 power 10 volt per meter per second. Here magnetic field is given by mu naught epsilon naught r divided by 2 into dE by dt, but C is 1 upon under root mu naught epsilon naught, so we can write mu naught epsilon naught is equals to 1 upon C square. So B will be equal to R or D upon 2C square into dE by dt. R is 1 into 2, C square will be 9 into 10 power 16 into d by dt is given 10 power 10. Simplify this, we'll get B is equals to 5.56 into 10 power minus 8 Tesla. So option 1 is correct option. In question number 6, the flux linked with a closed circuit of resistance 10 ohm varies with time t according to the equation phi is equals to 6t square minus 5t plus 1. We want to find the magnitude of induced current at t is equals to 0.25 second. Here the EMF is given by minus of d phi by dt, that will be minus of 6 into 2, that will be 12 t minus 5. So E will be minus of 12t minus 5. We want to find electric field at t is equals to 0.5. So 12 by 4 minus 5. So EMF will be 2 volt. I is V by R, that is 2 by 10, that is equals to 0.2 ampere. So option 4 is correct option. In question number 7, a field of strength phi into 10 power 4 divided by pi ampere per meter per turns act at right angles to the coil of 50 turns, and the area of coil is 10 power minus 2 meter square. The coil is removed from the field in 0.1 seconds. We want to find the induced EMF. The induced EMF is given by magnitude will be delta phi by delta t. Here, as the coil is completely removed from the magnetic field, the final flux will be 0. So delta phi will be equal to NBA divided by delta t. Here B is given by mu naught h, that is 4 pi into 10 power minus 7 into 5 by pi into 10 power 4. So B will be equal to 2 into 10 power minus 2. Put this value, n is 50 into 2 into 10 power minus 2 into area is 10 power minus 2 divided by delta t, that is 0.1 second, 10 power minus 1. Simplify this, we will get EMF is equals to 0.1 volt. So option 1 is correct option. In question number 8, it is given that a coil has 1000 turns. So N is equals to 1000 and area of coil is 500 centimeters square, that is 500 into 10 power minus 4, 5 into 10 power minus 2 meter square area. The plane of coil is placed at right angles to the magnetic field of induction. Here, if this is magnetic field, then plane of coil is at right angles. So angle between area vector and magnetic field will be 0 degree. The magnetic field in the region is 2 into 10 power minus 5 Weber per meter square. Now the coil is rotated through angle 180 degree. So theta 2 will be equal to 180 degree in time 0.2 seconds. We want to find the average induced EMF in the coil in millivolts. The induced EMF is given by minus delta phi by delta t. That will be minus of phi 2 minus phi 1 by t. Phi 2 is the NBA cos theta 2, that is cos 180 degree, minus NBA cos theta 1, that is cos 0 degree, divided by t. So A will be 2NBA divided by t. Number of turns are 1000 into B is given by 2 into 10 power minus 5 into area is 5 into 10 power minus 2 divided by time is 2 into 10 power minus 1. So EMF will be 10 millivolt. So option 2 is correct option. In question number 9, a closed circuit coil with resistance R is placed in magnetic field. The flux linked with the coil is phi. Now the magnetic field is suddenly reversed in direction. We want to find the charge that flows through the coil. Here the induced EMF is given by delta phi by t. E can be written as I into R is equals to delta phi by t. But I is equals to Q by T. So R to delta phi by T. This T will get cancelled out. So we can write R is equals to delta phi by Q. Here so we can write Q is equals to delta phi by R. Here, as the magnetic field is reversed by 180 degree, the change in flux will be 2 phi divided by R. So option 3 is correct option. In question number 10, a thin circular ring of area A is perpendicular to uniform magnetic field of induction B. A small cut is made in galvanometer and it is connected across the ends since the total resistance is R. Area is A and magnetic field is B. Now the ring is suddenly squeezed to zero area. We want to find the charge flowing through the galvanometer. Charge flowing through the galvanometer is given by delta phi by R. Here suddenly the ring is squeezed to zero area, so final flux will be 0. So we can write Q is equals to phi divided by R, and phi is given by BA by R. So option 2 is correct option. In question number 11, an aeroplane with wingspan D is equals to 50 meter is flying horizontally with speed of 360 km per hour. That is equal to 360 into 5 by 18 meter per second. So V will be equal to 100 meter per second. At that place, the vertical component of the Earth's magnetic field is 2 into 10 power minus 4 Weber per meter square. We want to find the potential difference between the tips of the wings. Here, the electric field can be given by V into B. So E is equals to velocity is 100 meter per second and B is given by 2 into 10 power minus 4. That will be 2 into 10 power minus 2 volt per meter. But E is equals to potential difference V divided by D, that is equals to 2 into 10 power minus 2. So V is equals to into 50. So V will be equal to 1 volt. So option 1 is correct option. In question number 12, the horizontal component of Earth's magnetic field is 3 into 10 power minus 4 Tesla and angle of dip 10 delta is given by 4 by 3. A metal rod of length 0.25 meter is placed in north-south position and is moved at constant speed of 10 centimeter per second, that is 0.1 meter per second, towards the east. We want to find the EMF induced in the rod. Here the rod is placed along north-south and it is moving along the west. Across the rod, the motional EMF will be induced, and for the induction of motional EMF, the vertical component of Earth's magnetic field is responsible. So we can write 10 delta is equals to BV by BH. So BV will be equal to 3 into 10 power minus 4 into 4 by 3. That will be equal to 4 into 10 power minus 4 Tesla. The motional EMF is given by BVL. So B is 4 into 10 power minus 4, V is 0.1 and length is 0.25. Simplify this, we'll get E is equals to 1 millivolt. So option 2 is correct option. In question number 13, a metal bar of length 1 meter falls from rest, that means its initial velocity is 0, under the action of gravity, remaining horizontal with its ends in east-west direction. This rod is falling downwards. We want to find the induced EMF at the instant when it has fallen for 10 seconds. Here the EMF will be induced due to motion. So motional EMF is given by BVL. Here the component of magnetic field that is perpendicular to both V and L will be BH. So E is equals to BH into V into L. Here V will be the velocity of rod at t is equals to 10 seconds. V is equals to U plus AT. Here U is 0, acceleration is 10 and time is also 10 seconds. So V will be 100 meter per second. Given BH is equals to 1.7 into 10 power minus 5 Tesla. V is equals to 10 power 2 and length is 1 meter. So EMF will be 1.7 millivolt. So option 3 is correct option. In question number 14, a cycle wheel with 64 spokes is rotating with n rotations per second. Omega is n RPM. At right angles to horizontal component of magnetic field. In this case, the induced EMF is capital E. If the number of spokes is reduced to 32, then what will be the induced EMF? Here, the EMF depends only on length of spoke and the angular speed. As both of them are remaining constant, the EMF will be same, that is E. So option 1 is correct option. In question number 15, a conducting square loop of side L and resistance capital R moves in its plane with uniform velocity V as shown in figure. A magnetic field induction B constant in time and space pointing perpendicular to it and into the plane of loop and the magnetic field exists everywhere. We want to find the current flowing through it. Here, if we check the induced EMF is delta phi by delta t with minus. Change in flux is BA cos theta, delta of BA cos theta by delta t. Here magnetic field is constant, A is also constant and theta is also constant. So there is no change in flux. So induced EMF is 0. So current will also be 0. Option 4 is correct option.